All right, so lesson 6 looks at polynomial identities. So an identity is an equation that is true for every value of a variable. And these identities have to be proven that they work for every case, regardless of what I substitute in for the variable. So we've been working with polynomial identities. We just haven't formally called them identities. So some examples are the sum and difference of squares, or the difference of squares, the sum and difference of cubes, a plus b quantity squared, the perfect square trinomials. Those are all polynomial identities because I know that if I plug any value in for a and b, I'm going to get that same output back. So to show or verify that an equation is in fact an identity, you start with one side and you algebraically manipulate it to be the other side. You do not treat it like an equation. And that's the biggest thing that trips people up with identities, is that they think because they see an equal sign that they can solve this like an equation with it's just a lot of variables. And that's not the case. What you need to do is pick a side, start with it, and then apply all the algebraic properties that you know to then go ahead and then show that it is in fact the other side. So if you're asked to show or verify that an equation is identity, you can assume that it is an identity. If you're asked to determine if an equation is an identity, then you have to do all of the algebra and then determine, can I get it equivalent to the other side? Okay, so I'm going to start with the sum of two cubes. So a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. We're going to verify that this is a polynomial identity. So I'm going to start with my right side. I'm going to start with this more complicated side. So I have a plus b times a squared minus ab plus b squared. Okay, and I'm now going to show that I can get a cubed plus b cubed from this. So this is just multiplying two polynomials together. So if I distribute that binomial to the other trinomial, algebraically, I get a times a squared minus ab plus b squared plus b times a squared minus ab plus b squared. And then we know we're going to distribute that variable to the entire trinomial. So a times a squared is a cubed. A minus times negative ab is minus a squared b. A times b squared is plus ab squared. So I distributed that. And I'm going to do the same thing with the b. So that gets me then plus a squared b minus ab squared and then plus b cubed. So I just did that distribution of the that binomial. And so now what I'm going to do is I'm going to collect my like terms and combine them. So I have negative a squared b and positive a squared b and ab squared and negative ab squared. So if we see when I combine those like terms, they all cancel each other out. And that leaves me with a cubed plus b cubed. And now I have shown that I am able to get that other side. So I have verified that that is an identity. And again, notice that I didn't add or subtract a cubed or b cubed. I manipulated one side and did all the math to show that they are in fact equivalent no matter what. Okay. So next one, I want to verify this polynomial identity. So x squared plus y squared plus z squared plus 2 times xy plus xc plus yz is equal to the quantity of x plus y plus z squared. So with this, I'm going to do the exact same thing on the right side. So this is two trinomials. So I can remember that x plus y plus z squared is really equal to x plus y plus z times x plus y plus z. Okay, and now I can, again, this is a trinomial times a trinomial, so I can distribute one trinomial to the other. So I have x times x plus y plus z plus y times x plus y plus z plus z times x plus y plus z. And now I'm going to distribute all that out. So x times x gets me x squared plus xy plus xz plus xy plus y squared plus yz. And then distributing that z gets me plus xz plus yz plus z squared. So now I want to go ahead and see what like terms I can combine. So that gets me xy and then xy. And then I have xz, xz, and then I have yz, yz. So combining those like terms, I get x squared plus y squared plus z squared plus 2xy plus 2xz plus 2yz. And if I take a look at these last three terms, I can go ahead and factor a 2 out. And so then that is going to get me the other side, x squared plus y squared plus z squared plus 2 times the quantity xy plus xz. Plus yz. And then I've shown, again, that I started with this side and I was algebraically able to manipulate it to the other side. So I am done with my identity proof. These are kind of like the proofs of algebra. I know you did proofs in geometry. These are like the algebraic proofs. This is kind of showing how one is the other with all of the properties, okay? Okay, now we're gonna determine if I have an identity here. So if I start with my left side, again, I need to see when I apply all my algebraic properties, do I get the other side? So I have 2a squared plus b cubed times 2a squared minus b cubed. So this is just a binomial times a binomial. So I know that I can just, again, distribute. So 2a squared times 2a squared is 4a to the fourth. 2a squared times negative b cubed is minus 2a squared b cubed. Now distribute b cubed. So b cubed times 2a squared is plus 2a squared b cubed. Plus. And then b cubed times b cubed is going to be b to the sixth, applying that exponent. Okay. And now I look at my like terms. So I can combine those two, and they're going to cancel each other out. And that leaves me with 4a to the fourth minus b to the sixth. And I take a look, that is not equivalent to 4a squared minus b cubed. So we say that this is not a polynomial identity. Okay, because I was unable to manipulate one side to get it equivalent to the other. Okay. All right, here we go. Number 4, determine if the following equation is an identity. So again, we're just going to take a look at that more kind of complicated right side, distribute the binomial to the trinomial. So I have x squared plus y squared, and that's times x to the fourth minus x squared y squared plus y to the fourth. So I know that if I distribute that, I get x squared times x to the fourth minus x squared y squared plus y to the fourth. And then that's going to be plus y squared times that entire trinomial, x squared y squared plus y to the fourth. And now I'm going to multiply, so I'm going to distribute that out. So this gets me x to the sixth minus x to the fourth y squared plus x squared y to the fourth. And then distributing out y squared, that gets me plus x to the fourth y squared minus x squared y to the fourth, and then y squared times y to the fourth is y to the sixth. Go ahead, combine my like terms. So I have negative x to the fourth y squared, positive x to the fourth y squared, and then x squared y to the fourth, negative x squared y to the fourth. So when I combine my like terms, we again see that those zero out, and that leaves me with x to the sixth plus y to the sixth. And I have now shown algebraically that I do get my other side. So we say that the equation is a polynomial identity. Okay. Because again, I was able to show that one side was equivalent to the other. Number 5. So in your brains, there's kind of a couple different ways that we can do this. I'm going to start with the right side, and you're going to see why. So I have ax minus by quantity squared plus bx plus ay quantity squared. So remember that this is just the perfect square trinomials. So I'm going to be applying, just remember that a minus b squared equals a squared minus 2ab plus b squared. Okay, and then I have that a plus b squared equals a squared plus 2ab plus b squared. Okay, but if I want to show this, again, by an identity, I do need to show it step by step. So I have ax minus by times ax minus by. And then I'm going to be adding bx plus ay times bx plus ay. Okay. And so now I can distribute one to the other. So ax times ax is a squared x squared. And then this is going to be minus ax times by. And then I get minus ax by again. And then plus b squared y squared. So that is, again, doing the binomial distribution to that first part. And now I can do the same with the second part. So I have bx times bx, so that's plus b squared x squared. Bx times ay is plus ax by. Again, because we know that multiplication is commutative. And then I have plus ax by again. And then plus a squared y squared. So that is multiplying out all of that second set of binomials. Okay, so now I can go ahead and I can combine my like terms. So I have negative ax by, positive ax by, positive ax by. So those will all zero out. So that now leaves me with a squared x squared plus b squared y squared plus b squared x squared plus a squared y squared. Okay, so now the thing with identities is you can kind of look at the other side and see what the end goal is and see kind of where you need to go from there. So I know that I'm going to want to somehow group a squared and b squared, and I'm going to need to group x squared and y squared. So I'm thinking that we need to somehow do factoring by grouping, and we need to manipulate this to show that we can do factoring by grouping. So since addition is commutative, I can rearrange however I want. I'm going to rearrange this as a squared x squared plus a squared y squared. And then I'm going to add b squared x squared plus b squared y squared. Because now what I can do is I can apply factor by grouping that we've been talking about. Group my first two, group my second two. And then if I take a look of my first two, I can factor out an a squared, which then leaves me x squared plus y squared. And then in my second two, I can factor out a b squared, leaving me x squared plus y squared. And then when I apply the factoring by grouping, I factor out that common binomial. That gets me a squared plus b squared times x squared plus y squared. And I have now shown that those two are equivalent and that they are, in fact, an identity.